In this video, we're going to go over the more general method for calculating the free energy change associated with a reaction. The other way only works for standard conditions. This one applies at all conditions. And the way we do that is by using the Gibbs free energy equation. Delta G equals delta H minus T delta S, where delta H is the enthalpy of the reaction, delta S is the entropy change of the reaction, and T is the temperature in Kelvin. Some helpful tips. First, keep very careful track of your negative signs. This is by far the most common error that I see. Make sure that you're putting the values in from the tables that you get them from correctly, and whenever you are subtracting a negative, you flip that into addition instead. You want to also make sure to convert your entropy term from joules per Kelvin to kilojoules per Kelvin before plugging it in. This is the second most common error that I see. Lastly, you will probably need to use Hess's law and some tabulated values to calculate delta H and delta S. Let's look at an example. We're going to calculate the delta G reaction for the following process at 298 and 1450 Kelvin. This is iron oxide solid plus 3 hydrogen gas becomes 2 iron solid plus 3 water. This is one of the ways that we can smelt iron ore. The delta H values for each of these substances and the standard molar entropy is given below in the table. If you would like to take a few seconds, a few minutes, and try working this problem out for yourself, go ahead now. Our method. We're first going to calculate the delta H and the delta S for this reaction from the given values. Then we're going to convert that delta S into kilojoules per Kelvin, and then we're going to plug all of that into the Gibbs free energy equation and solve. Let's begin with delta H reaction. It equals, in parentheses, 2 times 0.0 for the iron term, plus 3 times negative 241.8 for the water, end parentheses, minus, in parentheses again, minus 824.2 for the iron oxide, plus 3 times 0.0, end parentheses. That last one's for the hydrogen. Note that both of our pure elements in their native states have delta H of formation of 0. If we do our crunchity crunch, we get that our final answer for the delta H is 98.8 kilojoules. This tells us that this process is endothermic, and the units of delta H reaction are now kilojoules rather than kilojoules per mole because we multiplied each of those heats of fusion by its molar coefficient. Let's try the entropy. Delta S for this reaction equals, in parentheses, 2 times 27.3 for the iron, plus 3 times 188.8 for the water, end parentheses, minus, in parentheses, 87.4 for the iron oxide, plus 3 times 130.6 for the hydrogen, end parentheses. Note that all of these molar entropy values are positive. That's because molar entropies are always compared to absolute zero, where there is zero entropy. Let's crunch our numbers. At the end of our crunching, we get 141.8 joules per Kelvin, but we're not quite done yet. We're going to convert that joules per Kelvin into kilojoules per Kelvin through the conversion factor of 1,000 joules in 1 kilojoule, giving us a final entropy value of 0.1418 kilojoules per Kelvin. This process represents an entropy gain. The moles unit drops out once more, and we've converted into the correct energy units before moving on. A reaction with a positive delta H and a positive delta S is predicted to be spontaneous at high temperatures only. Let's see if that's true. We're going to begin by calculating delta G at 298 Kelvin. Delta G reaction equals 98.8 minus 298 times 0.1418. Crunch our numbers down. We find that delta G reaction at this temperature is 56.6 kilojoules, meaning this reaction is non-spontaneous, and rather strongly so. At 1450 Kelvin, on the other hand, our delta G will equal 98.8 minus 1450 times 0.1418, giving us a delta G of minus 106 kilojoules, and therefore spontaneous under these conditions. So there you have it. If you're trying to use the Gibbs free energy equation, first calculate your delta H and your delta S. Make sure that your delta H and delta S are in the same units. Plug them into the free energy equation and just crunch your numbers. There you go.